So this will be our last topic of under E124 electrical circuits 2. And this is unit 7. It's the analysis of two port network. So these are our learning outcomes. And the student must have done these following outcomes after this unit. So first, you must have calculated the network parameters in a two-port network, and we'll be discussing those different parameters, and also identify the different models of a two-port network, and we'll be using those parameters to model a two-port network. And lastly, draw the interconnection between different two-port networks. So if we start with the definition of a two-port network, a two-port network. So from its name, port means this is a pair of terminals. So when we say a two-port network, it has a two pairs of terminal. A single resistor, this one can be considered a single port network. Single resistor, a single capacitor, and a single inductor. They can be considered single port network because they only have one pair of terminals. Now, if you combine them, for example, if you have a T network, most common um, network that we have, the T network, here we have actually two ports. So we call this one a two-port network. And usually we draw a block to model that network inside this block. And in this unit, we'll be focused on that type of circuits or networks, a network that has two ports or a pair of two pairs of terminals. And those terminals here, we can apply some excitation. Voltage can be a voltage source, and it can also be a current source. And take note that a two-port network, inside the two-port network, it only contains, it's a linear network actually. Linear network. So meaning it contains linear component like this resistor, this capacitor, and this inductor. And also it's not possible. It cannot contain independent sources inside. Independent sources. So meaning you cannot have a source inside a two-port network. We cannot call that one a two-port network if there's a voltage source, a current source, or whatever independent source. But you can contain dependent sources. So we already discussed what's the difference between these two independent sources and dependent sources. It can be current source, it can be a voltage source, or whatever. So that's a two-port network. So let's start with the first model or the first parameter. We call it the impedance parameter. Impedance parameter. So impedance, so this is Z. We use the variable Z to represent this impedance. And now if you take a two-port network, let's say this is the two-port network. We have a linear network here. Linear network. That is a two-port network. It has two pair of terminals, the left and the right. Then we can have a voltage here. We can call this one V1, voltage V1. Then we can have another voltage at the other side. And we can call this one V2. So for the voltage V1, it has resulted with the current I1. And for also the voltage V2, it results to a current I2. So this is a simple linear network. Now, in a impedance parameter or model, the voltage and the current can be represented by these equations. We can solve for V1. That V1 is just equal to a certain impedance. You can just call it Z11. Later on, we'll be solving those parameters multiplied by I1 plus Z12 multiplied by I2. And for the second voltage, V2, so it'll be Z21 multiplied by I1 and plus Z22 multiplied by I2. So in matrix form, we can write this one in matrix form. So V1, V2 is just equal to certain impedance parameters. Z11, Z12, Z21, and Z22. Then you multiply it by the input and output currents, I1 and I2. So this is the model for a Z parameters model. Now, if you want to model the network into a Z parameter model, so we need to find these parameters. These are the Z parameters. So how do you find these Z parameters? But before we do that, we can define these parameters first. Z11, we call this one the open circuit input impedance. Open circuit input impedance. Then we have Z12 is called the open circuit. Z12 is called the open circuit transfer, call it the transfer impedance. Transfer impedance from port 1 to port 2. So that's the direction of Z12 from port 1 to port 2 transfer impedance. For Z21, it's the other way around. It's still an open circuit transfer impedance, but this time this is from port 2 to port 1. Then finally, for the last one, Z22, this is the same as Z11. It's open circuit, but instead on the input side, because it's Z22, the number 2 represents the output. So this will be the open circuit output impedance. So based from this definition, we can use them to solve for these parameters. So first, for Z11, if you want to solve for Z11, Z11 is just equal to, you take V1 and you divide it by I1. But taking sure that I2 is equal to 0. You make I2 equal to 0, then you divide V1 with I1, that will be Z11. What does it mean? It means, how do we make I2 equal to 0? Here, so if you look at the diagram, this is I2 here. So how do we make it to 0? We just make it an open circuit. When an open circuit, the current is equal to 0. So we just remove the output in this part, remove this one, then divide V1 in I1, and that will be our Z11, and that is called the open circuit input impedance. That's why it's called open circuit input impedance, because we're looking at the impedance at the input side by removing the output. For Z21 or Z12, let's say Z12, so put here. So for Z12, we're dividing V1. So there's a pattern here. If you look at the formula, voltage is always on the numerator because this is an impedance. Impedance is just equal to voltage divided by the current, according to Ohm's law. And if you look at the subscript, when I'm solving for Z11, my subscript for the voltage is 1. my subscript for the current is also 1 because it's Z11. Then for Z12, if you look at our formula again, 1 is the subscript for the numerator, which is the voltage, and 2 will be the subscript of the numerator I. And here, because there's an I2 in the formula, what we make 0 will be the I1. We will make I1 be equal to 0. So it means you make it open circuit in the input side and solve for V1 and I2. You divide that, that will be Z1, 2. Later on, I'll give you more example to illustrate these formulas and how to use them. Next, for Z12, then Z21 for Z21. So based from the pattern, there's a pattern again. This will be V2 divided by I1. Then there's an I1 there. Let's make I2 be equal to 0. Then for Z22, same thing, V2 over I2. But this time, I1 will be equal to 0. So these are some formulas that we'll be using to solve for the Z parameters. And to illustrate that, or before we do that, there are two types of these parameters or two-port network. And we call them, the first one, we call it symmetrical. These are characteristic of two-port network. A network is symmetrical. When we say symmetrical, this implies that the network is symmetrical, or other term is mirror-like. Mirror-like. So the other half is similar to the other half. It's divided in between by a certain parameter or something. Then the left should be similar to the right. And if that's the case, then the network is called symmetrical. And this happens in a Z parameter network. This happens when Z11 is equal to Z12. So the system is symmetrical if Z11 is equal to Z12. Another characteristic, they call the reciprocal. The reciprocal network. Reciprocal. The network is reciprocal. When we say reciprocal, this means that if you interchange the sources, the output and the input, the transfer impedance or the transfer impedance remains the same. Remains the same. And for Z parameter, this happens when Z12 is the same as Z21. The system or the network is a reciprocal network if Z12 is equal to Z21. It's a symmetrical network if Z11 is just equal to Z12. So these are just common terms that we used in a two-port Z parameter network. So now let's take an example to illustrate, or before that, if you look at the model for a Z parameters, where the T equivalent circuit for a reciprocal case will be look like this one. So it's a T model network. This Z can be any impedance, not only a resistor, but it can be any value. It can be a complex number. Here, this will be Z11 minus Z12. Well, this one is Z12 and this one is Z22 minus Z12. So this is a T equivalent for a reciprocal two-port network. Now let's take an example to illustrate this. Example. Determine the Z parameters. of the circuit. So let's take a simple T network circuit. Just a resistor T network here. So this is a two-port network. Let's call this one, let's use 200 ohms. This one 300 ohms. And this one 400 ohms. Now model this one into a Z parameter model. So we need to solve for the Z parameters. First, we start with solution. We start with Z when. So again, the definition of Z when, this should be equal to, we can apply voltage here. This will be our V1. This will be our V2. So we have a current here, I1. Then a current here, I2. So for Z11, again, the formula for Z11, because it's 1 and 1, it will be V1 over I1. Then we'll be making I2 be equal to 0. So in this case, we will remove this part. So this will be an open circuit here. So if this is an open circuit, I2 is equal to 0, so there will be no current here. So if there will be no current, all the currents will go here. So this is also be equal to I1. So there's no current going to the 300 ohms. So if I solve for I1 is just equal to the voltage V1, total voltage V1 divided by the total impedance, which is 200 plus 400. 200 plus 400. Why? Because they are in series. So we just remove this part here because it's open circuit. So we don't care about that part. So this is just the circuit that we're looking at when we solve for Z11. And if you look at that circuit, that's just a simple series circuit with resistance 200 and 400 ohms in series. So if I want to solve for the total current, it's just equal to the voltage divided by the total resistance, which is equal to 200 plus 400 because they are in series. So this will be V1 over 600 ohms. So if I solve for V1 will be equal to 600 times I1. So if we substitute this one here to solve for Z11, our Z11 will be equal to 600 I1, which is the V1 divided by I1. And if you can cancel that out, so therefore Z11 will be equal to 600 ohms. So this is our first parameter. Z11 will be equal to 600 ohms. Now for the second one, the Z12, if we solve for Z12, so the formula will be V1 divided by I2. So this time we'll be making the I1 equal to 0. So if we go back again to our circuit diagram here, so this time we'll be removing or making I1 be equal to 0. So if this is 0, then the voltage here will be just equal to V1. Still V1 because there's no current flowing through the 200 ohms. If there's no current, then therefore it's the same voltage. So that's the voltage across the 400 ohms. So again, we'll just remove this part, but take note that the voltage across the 400 ohms is actually V1. And that will be the key in solving our Z12. So if again, if we solve this one, V1 divided by I2. So we need to solve for I2 from the circuit. I2 is just equal to V2 divided by the total impedance. But this time V2 is not in the formula, so we don't need V2. So to remove V2, we can just use the voltage divider theorem. So V2 is just equal to V1, which is the voltage across, or let me replace this one. V1 will be just equal to V2 multiplied by 400 divided by 300 plus 400. That's voltage divider. That's the relationship between V1 and V2. We don't want V2, but we can relate V2 with I2. So this time, the I2 will be equal to V2 divided by the total impedance in series. That's 300 plus 400. So if we solve for V2, V2 will be equal to 700 I2. V2 will be equal to 700 I2. Then if we can substitute here, then we have a relationship between V1 and I2. So solving for V1, V1 now will be equal to 700 I2 multiplied by 400 divided by 700. And we can cancel out that 700. So therefore V1 is equal to 400 I2. Then we can now solve for our Z12. Z12 is equal to V1, which is 400 I2 divided by I2. Then we can cancel that out. So therefore Z12 will be equal to 400 ohms. Next, for Z21. For Z21, we can repeat the process again. This will be equal to V2 divided by I1, and we're making I2 be equal to 0. So go back to the circuit. If we make I2 be equal to 0 and we make, it's the same process, we can make the voltage across 400 ohms again be equal to V2. But this time I will not be using the voltage divider because it's a long way to use that one. We can just directly solve the voltage across the 400 ohms, and that's equal to V1. In this case, V1. So V1 will be, this is I, wait, or this will be equal to V2 because I2 here will become 0. So let's just erase this first. So I2 will be equal to 0. So if that's the case, this will be equal to V2. So the voltage across the 400 ohms is V2. But I know, so without using the voltage divider, it's a simpler way to solve this one. I know that the current flowing through the 400 ohms is also I1. So from that, we can say that V2 is just equal, that's the voltage across 400 ohms. By Ohm's law, we just need to multiply 400 with I1. We just need to multiply that by I1 because by Ohm's law, the voltage across the 400 ohms is just equal to the current that flows there, which is I1, multiplied by its resistance. So therefore, V2 is equal to 400 times I1. So Z21 now will be equal to 400 multiplied by I1 divided by I1. Cancel that out. Z21 is also equal to 400 ohms. And finally, for Z22. Z22 is V2 over I2 when I1 is equal to 0. So again, I1 is equal to 0. It's similar to Z11. So if this is equal to 0, we remove this part here and we only look at this part here. So again, that's just equal to a simple series circuit with 400 and 300 in series. The current is I2 and the voltage is V2. So therefore, V2 is just equal to the current, which is I2, multiplied by the total impedance, which is 300 plus 400, or simply 700 I2. We substitute that here. Z22 now will be equal to 700 I2 times I2. So therefore, Z22 is just equal to 700 ohms. Okay, so this is the first. So if we draw now the conclusion, the Z parameters, usually we use the matrix to write this one. This is Z21. So Z11 is here. So this is 600. Then we have Z21 and Z12, 400, 400. Then we have 700. So if you look at the circuit, so this is the final answer. This is the Z parameter. the equivalent Z parameter of that network here. So if you look at this network, we can conclude that because Z12 is equal to Z21, it's equal to 400 ohms. So we defined that before. When that happens, Z12 is equal to Z21, then the circuit is, or the network is a reciprocal network. Okay, so this is the first model for the two-port network. We'll be discussing the other types in the next discussion.